Hello, everybody. Welcome to the second session of the Big Tech Day. Welcome also to our guests joining online through the live stream. And I have a question for you. Don't you hate that feeling when you're writing a text message and trying to find the right emoji just to round it up in the end, just to find yourself endlessly scrolling looking for the right one? In that case, today is your lucky day. Our next talk is titled Finally Understanding Embeddings, and you will never have to search for the right emoji again. Big promise. Joining me on stage are Elias Schecke and Dennis Schulz, two brilliant minds of TNG's innovation hacking team. Elias is a senior consultant and my fellow TU Berlin mathematics alumnus, where he wrote his thesis on applying evolution strategies to mixed integer linear programming. And these days he applies that same mathematical precision to build cutting-edge RAG systems and AI showcases like the one you will see shortly. Dennis here is also a senior consultant and holds a PhD in low-temperature physics from Heidelberg, but he's far more than a scientist. He's also a Science Slam champion, a published author, and he even hosted a scientific TGV show back in the day. And at TNG's innovation hacking, he fine-tunes embeddings and mines data to turn AI theory into tangible tools. And today, these two here will demystify embeddings for you without drowning you in jargon and show you how to match words with embeddings using semantic search. And you'll leave understanding why words are turned into vectors, which benchmarks really matter, and how to scale your semantic search application. One more note from my side, please hold your questions until the end of the session. We will have time for a Q&A. And for the guests joining through the Zoom, you can just put your questions in there, and we will find time in the end also to address those. And now, without further ado, welcome Elias and Dennis.
Welcome. Thanks to see that nice turnout. That's lovely. We would love to talk about embeddings today. We would like to give you a feeling for what they do, how they are, and also, we will talk a lot about emojis. But to start off, let's start off with a simple task. Elias, you have a few, images here, and you have an empty two-dimensional plane. Could you maybe try and place all of these somehow on this plane in a way that makes sense to you?
Okay, quite a broad task. Let's see. Let's start in the middle here. And maybe we could place a bird somewhere on top of a human because it's flying in a sense, and a fish it's swimming in the sea. So this could be something like below sea level, so below the human. A bird sings, so let's place it kind of next to the bird, and the best companion of a human is a dog, so let's place it here on the ground level. And okay, now it's getting a little bit harder. A dinosaur, I would place it maybe next to the bird because they're related, but I feel like two dimensions don't cut it anymore because not all dinosaurs fly, so I don't know, let's place it somewhere here. And the wave is easy again. It's kind of has this musicality of a sound, and it's also related to the fish, so somewhere in between music and the fish.
Yeah, wonderful. Yeah. Thanks a lot. And what we have done here is basically the first embedding. This is a very simple two-dimensional embedding, and Elias, as you noticed, started assigning kind of abstract concepts to the two dimensions. So the x-axis was a relatedness in a biological sense, I guess. And the y-axis was distance from ground level, something like that. But you also noticed that at some point there was this thing of, oh, damn it, I would love to have some more dimensions to put stuff in. So let's lock that choice in. In this two-dimensional embedding, Elias placed all of these abstract concepts in a plane. And for example, according to him, dinosaurs are as close to dogs as humans, which is a choice. I mean, wonderful, that works. But as you see, we already have this thing. So this is abstract concepts, kind of a dictionary of abstract concepts. You can just describe all of them as a vector. So this is an embedding. You can also start to measure distances between the concepts and then somehow understand what the distance between concepts here is. So that's cool. And of course, would be nice to add more dimensions, maybe a third dimension, maybe a few hundred more dimensions would also be lovely. And this is an embedding. Let's quickly dive into the history of them. The first really successful model was Word2Vec. That was around 2013, developed by Google, which is this simple idea of taking one word and just associating one vector with it. It's a simple dictionary, and these vectors then have hundreds of dimensions that can represent some abstract concepts or something else. Hard to say. You know, that's the idea. How do you get these exact vectors? There's two ways to get to them. First, you make a list of all the words that you want to embed. Then you assign random vectors to them. And then, for example, the idea could be that if you have a sentence here, you want all the vectors of a sentence to add up to the missing word in the sentence. So this is a way you could train it. Or alternatively, you could say, it would be nice if all the words that are next to each other in a single sentence have embeddings that are kind of close to each other. Either way, this is how you get to this Word2Vec dictionary. There is a very obvious limitation, and the limitation is exactly in this example sentence that we've chosen here. Make a right turn now can mean right in right and left. It can also just give you the advice to do the correct turn. Right is a word that has different meanings. And that's a problem if you have different semantic meanings that are unfortunately through language expressed through the very same word. And this is where a new technology came in, a technology called transformers. And I will now give you the most hand-wavy explanation of attention that I am able to. Attention is basically the idea that you take a sentence and then you let the sentence embeddings soak in each other so that the whole sentence takes all the meaning of the entire sentence in itself. And then you also use this end of text token. And this end of text token also gets all of these embeddings and then at the end kind of uses all of the meaning, has all the meaning of the sentence in it. Let's see how this looks graphically. This is a lot of, this happens, but actually this happens. So all the words influence each other. Ideally, the words that have high relation to each other influence each other stronger. And then you go through several layers of this, and bam, you have an embedding for the entire sentence that is kind of just ended up here. Yeah, that's it. And that gives us a first, embedding vector that we could work with, and maybe we could actually start working with that, right?
Yeah. So one very popular application here is semantic search. And if you think of a search engine like Google, you typically type in a query string. So I'm looking for some documents, maybe like a Wikipedia article or something. And we can do the same. But we are here to get good emojis for a fitting text query. So we start with this text query. And I kind of had this concept of embedding earlier, where we talked about ground level, above and below, and also musicality. So again, I can just place this somewhere like on ground level, because dancing is usually done on the ground, and maybe to the right. And now I generated an embedding for my search query. And with this, it's quite easy to look for familiar concepts by just, again, looking at my query and calculating the distance to all of other concepts. Can be text documents, could be, in our case, emojis. And by this, retrieving the closest one will give me kind of a familiar concept. So we see that a wave is very related to dancing in my example. So I didn't do a quite well job. But we could also see that music is quite related. So that's better. So because I'm not a professional embedding model, we thought, let's just take one. And at TNG, we have a couple of ones available through our GPU cluster. For example, the general text embedding Qwen2 with 7 billion parameters. And I can just type in a search query here. Wanna go, dancing. And now we can calculate an embedding, and I also calculated the embedding of a lot of emojis. And we can kind of measure the distance and find the closest one. And let's see, if we look at our results here, we can see, okay, a dancing emoji is on the first and the second place. So this works quite well out of the box. You can also see on the right-hand side that 2D dimension doesn't really cut it because this model has more than 2 dimensions. How many dimensions does it have? Let's have a look. It's in the table there. So here you can see basically how much memory it consumes, how many parameters it has, and the bending dimensions. So now we're talking not about 2 dimensions, but 3,500 dimensions. So that's quite huge. And you can also see that there are other versions of embedding models that are quite smaller. So the one above is only 10% as big, and I could fit this on my local machine even. So how many dimensions do you really need in an embedding model? And there was recently a mathematical paper, and I kind of worked through this and translated this into having an embedding search model for emojis. So imagine having a lot of text queries that you want to find a right emoji for, and you have all the emojis you could think of. And for each query, you could think of assigning a value of 1 if it's a fitting emoji, and a value of -1 if you wouldn't recommend your parents to use this emoji with the text message. And this kind of gives you this nice motion of a query relevance matrix. And what the authors did, and what took me quite some time to understand, is they found a relation of needed embedding dimensions to perfectly retrieve those emojis with this mathematical term. And what this basically means is that you can embed as many as this polynomial documents to retrieve those perfectly. And because you probably don't want to do the calculations yourself, we prepared a little table here. So for example, to embed 500,000 documents, in theory, mathematical theory, not the reality, you would need at least 512 embedding dimensions. So let's say we are working with 250 emojis, maybe here. The models are too big, way too big. So we can go to the smallest one available to us, and we can run it on our device, and we can even maybe fine-tune it. Dennis, what do you say?
Yeah, sure. Let's do it. We checked, and we took this model to fine-tune. Now, the thing that we took is the thing that you can start out with. It typically is, for example, a so-called base model. Base models are models that have just seen a lot of literature, but don't know what to do with it. They have not been trained towards a specific task necessarily yet. So for example, if you ask a base model, this is just a random example, who are you? You would get an answer that is correct and perfectly fine. But if you then do some instruction tuning, if you go closer towards a chat model, you can, for example, build in stuff like a thinking phase. It suddenly knows that it was developed by Alibaba Cloud and stuff like that. So, this is the difference there. This is not the path we are going to take, though. We want to go towards training it for embeddings. And for embeddings, you first need some data to train on. And since we wanted to do that on our own laptops without going on a big cluster, we started out with 250 emojis. Which ones? Well, these ones. These are the 250 emojis. Now, those are, according to some website, the 250 most popular ones. So, you know, that's actually the top one emoji is that one, seemingly. So how do we get some training data? Of course, we could have just scraped all of our WhatsApp data and put it into this training model, which has several problems. Firstly, I only use double colon and close brackets and basically nothing else, but that all the time, so that's not the perfect data. A friend of mine recently said that his uncle finishes every single WhatsApp message with thumbs up and a flag of Sweden because he went to Sweden and liked it. So this is a problem with real data. The other problem is obviously that you might have a lot of data for the top 10 emojis. You might not have a lot of data for Apple or red flag, depending on who you check. So we went. So for that reason, we went with generating data. We generated all the data for ourselves by just giving the emoji to an LLM and asking, please give us 50 realistic messages. They should be funny, sarcastic, normal, whatever, long, short, just so to get a range, which means that then in the end we had a data set of a lot of chat messages. We mixed them together. How did it look? Let's take all of our favorite emoji, this emoji, the emoji, and then you have stuff like send help or don't. This is entertaining, and 50 other chat messages that go with it. And then that's basically cool for training. So what do? You give the chat message to the embedding, calculate the embedding for this one. You give the emoji to the embedding, calculate the embedding, calculate the distance, and then change it around so to make the distance smaller and smaller. Now, that probably works, kinda, but actually Gwen is instruction aware. It can take instructions, and it's super helpful to tell the intention, to tell what you actually want to do with the data. So what we actually did is we added an instruction query, which was, for this chat message, please give us the best fitting emoji. There was something around that. The answer query was the same, but emoji and chat message exchanged. And then you can embed this and give it to a model. But then there is this chance that possibly you just tell the model, hey, emojis are good. Whatever emoji, emojis are super good. Would be nice to actually also have a negative training. So we added a negative emoji. What would be a negative emoji to let's dance the night away? Well, the sleeping emoji would be a pretty negative emoji. Though if you think about it, that could be a sarcastic message. Actually, that could be pretty fitting. So we went away from trying to find the negative emoji for everything and just went with a random emoji, something like, I don't know, pig. Imagine getting, let's dance the night away, pig emoji. Would be confusing, doesn't fit. Perfect choice for the negative. So we have kind of a triplet, right? We have the statement, the anchor, and then a positive, and then a negative. And then what we didn't do yet, but what is perfectly possible as well, is you can then run through some training epochs and then check, the top 10 of emojis that you get back, and then you might see one that doesn't fit there at all, and then you can, add stuff to the training data that counteracts this behavior in particular. So that's just train against specific model problems, whatever that means. Like you can look at the outcome and then work against that. But that is then actually what we did. This was on these 250 emojis, and then we got this model that is called emoji embedding, and then we can give it a message like cannot talk right now, giving a talk. Let's see what it does. This is okay, I guess. I don't know. It's hard to say what's correct, right? Because it's such a subjective thing. Would be lovely to have a neutral way to look at it. Would be lovely to have some kind of benchmark. So let's talk about benchmarks. In general, there's a lot of benchmarks. There's the massive text embedding benchmark, the MTEB, online, where you can pick so many benchmarks, all kinds of, these are the categories that they have. Stuff like they have STS tasks, where you get sentences that are, rated how similar they are to each other semantically. Stuff like that. There's classification tasks. But we want to retrieve embeddings from a large list of embeddings. Cool. So let's do our own retrieval benchmark. We took a data set that wasn't seen during the training, quite typical. Basically gave it an emoji and the message, for example, when the autocorrect ruins your heartfelt text, asked for the best 3 emojis. Cool, that's in there, so that's a hit. I thought I'd impress my boss by volunteering for that big presentation. This emoji, not in there, that's not a fit. So this would be 50%. Now we run this like this, which basically means that the chat looks like a frantic YouTube live chat. My terminal was very colorful. Never had a terminal this colorful. And in the end, we get this, which is super cool. What can we see here? We did the top 3, which is 3 best emojis. We also did the top 10, just for good measure, 10 best emojis, which is obviously higher. So top 10 is this orange. In blue, you see the top 3. Down here, you see the epochs. One epoch is going through the full training data once. So we trained for about 17 epochs, and it became better. That's great, I guess. We also have these dotted lines here. That is, if you just use the pre-trained Gwen embedding model, the 06B, the same but pre-trained by Gwen, and we are about 2 times better than that in the top 10 and in the top 3. Well, wonderful. That's quite cool. The base model is somewhere down there. It's almost a random guess. For some reason, it thought that the Brazil flag was always the least fitting emoji for any text message. I don't know. One more small detail that really confused us during the training. We also, before we did the top 250 emojis, we did the top 10. Because that's how you start, right? You want to do it small at the beginning to then make, and it just didn't train. It just didn't work. Like, the training didn't start, the loss function never went down. And I think we understood it because these are the top 10 emojis, and there's just so many hearts in there that, the chat message, and it's so generic and so used by everyone that it's really hard to identify, this chat message is certainly the smiling face with hearts and not the double hearts that like fly around each other. So in green, you see the correctness of the top 10 emojis over time. And in purple, just as a comparison, those are the 240 to 250th most common emojis. And you can imagine, like, if you have a basketball-themed message, that's pretty easy to identify. That's doable. Okay, lovely. So, so far we've worked with texts and emojis, which are technically also texts. Can we somehow extend that to, let's say, images, maybe?
Of course. And yeah, why we did this is basically because we generated this very lovely images in the beginning to show you how embedding works. And we, of course, also want a model that can handle these ones. And there are even other websites like Emoji Kitchen where you can combine 2 embeddings. And we also wanted full Emoji Kitchen support at this point. So let's see how you can do this. There's a model out there was developed in 2021 called contrastive language image pre-training. That's the algorithm. And what this algorithm does is basically search the rep for images and corresponding labels. And you can see the variety of labels that you can find on a Wikipedia page about fish. It's range from it's a fish to like a very schematical view of how the heart pumps the blood through a fish, and there's a quite range. And you just go into the internet, grab all the pairs you can do, and then you use a new model architecture called Visual Transformer. And it's quite similar to what Dennis talked to you about, just that we exchange the words or tokens with patches of the image. And a patch is usually this square of 16 by 16 pixels, and you divide the picture into all of these patches, and then have a small embedding on these patches, and then use the normal attention mechanism of all the patches and their embeddings soaking into each other, the attention mechanism we saw earlier, and you come up with the same embedding as before. And you do the same thing for the query, the label, and just use the normal transformer there. And you will get two maybe random embeddings at the beginning because they're initialized randomly and they don't fit together yet. But then you go into training. And what you do is you build batches of, let's say, 16 images and their corresponding labels. And you pass the images through the visual transformer, pass the labels through the normal text LLM. And what you will get on the diagonal, you will find the distance of the corresponding pairs of image and their corresponding label. So this is something that you really want to minimize here, and everything else is a random pairing of image and a different label, and you want to maximize the distance of this. And with this, you can just train a model, and OpenAI did this in 2021 with 400 million pairs. Then Meta went in 2 years later with 2.5 billion pairs, but all of these were only English-based text. And there was a long time where you couldn't get over what they called the curse of multilinguality. Until this year, Meta mentioned it to have quite a huge amount of English training pairs, but also including a lot of other languages, like up to 300 languages there, which share a common distribution to the data, the English data they had collected. And this way, they were even able to scale this to that many languages this year. And we can just use this model and evaluate it against, let's say, our query from the start. Wanna go dancing. And what we see, we get quite good results here. There's a picture of a guy dancing, another guy dancing in this one, and a fish dancing. Okay, that's pretty good. And I think that's good enough for us. So now we have all these possibilities. And maybe you could embed all the images that you could think of. So that's quite a lot. It's not 250 anymore. And we have to talk about scaling at this point. Because if you think of our search in the beginning, it calculated the distance between a query and all of the images there. And what you do typically is you want to approximate the nearest neighbors, not calculate the distance to all of them. And an algorithm that is usually used there is hierarchical navigable small words. And you could think of this as having the emojis in a graph, and each node contains one emoji, and nodes are connected by edges, and these edges will kind of give you an intuition of this is close together. So similarity is connected by edges, and in order to navigate the graph properly, you want to restrict the number of edges a node can have. Let's say 3 edges is the maximum you can have to have this kind of sparse graph there. And this is one of the modifiable parameters if you want to do HNSW. There are a couple of more ones, so we figured let's go through a typical search, how this would work with the algorithm, and you can stand more of the parameters that you have to choose from if you want to set up this search. So now you see different layers, and that's basically because you want to navigate quickly in the upper layers and optimize for precision in the lower layers. So in the lowest layer, you will see here, you will have all your embeddings, all the pictures that you want to retrieve. And going up, there will be fewer and fewer, just so you can move quickly there. So at the first level, you will just start with a random point and calculate the distance to your search query. And because you have like close neighbors connected by these edges, you can also calculate the distance to each of the neighbors there. And then you come up with the closest one, and you move to this closest one and look for other neighbors that you could traverse the graph through. We don't have any anymore, so we can go down a layer. And there again, we have neighbors. We calculate the distances of these ones, and we collect all of the red nodes and their distances in a candidate list. But we don't want to store arbitrary candidate lists, so we need to cut off at some point. And this is the parameter called EF search that you can also choose. It's basically saying, let's say, EF search is 4 in this example, so we have to drop the 5th one, which is furthest away. And now we haven't found anything closer anymore, so we move down a layer. And now we reached the bottom layer. And there, as I said, we really want to not look at just one node, but all the candidates to increase the precision of our nearest neighbor search. So let's look at all and their neighbors. And you can basically see what we did is not having to calculate all the distances, because there are a lot of nodes that are not marked at this point. And we still found like very close ones. So now I'm happy to say that we could even, in theory, scale to like larger image databases at this point. To give you an overview, embeddings are not just semantic search. They're used by big players like Netflix and Spotify to recommend you some music tracks and also do some recommendations on movies, for example. And they're used by Uber and eBay for some fraud detection in financial transactions. There, Uber played around with graph neural networks that generate these embeddings that I touched in my thesis. But yeah, that's it for today. So I hope we showed you that embeddings are quite more than just this concept, that you could understand it a bit, and that you see how lovely they are if you mix them up with embeddings, with emojis. Thank you.
Yes, thank you very much for this very insightful talk and colorful demonstration. So now is a time for questions. So anyone having questions, please.
Yeah, how exactly are the emojis tokenized? You said they are text, so are they just this ASCII transcription? Or?
Yeah, it's Unicode encoded, and if you ask, for example, ChatGPT to write your report, you will sometimes, if it has to be like a LinkedIn post or something, you will also find these emojis in there. So those aren't pictures, this is just Unicode text, and those models are trained to also use this Unicode text. Yeah.
Hi, thanks. Great presentation. I wanted to ask that you were talking that you had issues with the hard classification, that in the top, I don't know, 10, you had hearts and they had ambiguity. And how did you work around this? What was the solution in your case?
If you take 250 of those, you know, like, we didn't. I was frustrated. And then, you know, like, it was super the first step was actually that we did this 250 emojis and it worked great. And then was like, let's just do a 100 best emojis. Probably it's greater. And then it got worse. The model got worse in the benchmark. And I was like, what is happening? And I think it is because it's ambiguous. I think the emojis are just ambiguous. So in that particular toy model, we did not work around it. You surely could by setting the negatives. I mean, the thing is that for this training, we set the negative emojis randomly, which means that there probably were a lot of sentences where you had a lovely sentence and then a heart, and the negative was also a heart. And then, but a different one. And then probably that just doesn't work. So probably you would need to hand select your data, which we didn't do.
So do the dimensions have any meaning if you try to, analyze them? And also I was wondering about the optimization, like, is it just like an autoencoder, or how does it, for example, guarantee orthogonal dimensions and good principal components? Is there like something there that takes care of that?
So in the introduction, we kind of showed you these very clear dimensions, right? Above groundedness and so on. In reality, it's not that simple, to be honest. It's kind of random. There is some research into explainable AI there that kind of wants to find distances in between embeddings, and also explaining that you could, for example, come from a king and move to a queen, which has the same direction as moving from a man to a woman. So there is some sort of direction of meaning, but it's not that clear how these dimensions look like. Yeah.
There's also this thing that it doesn't work in 3 dimensions, but the more dimensions you add, I mean, it's cool. Like if things are perpendicular, you can, like, explainability, I don't know, but like just the way to imagine, like perpendicularity means that you can have 2 concepts, 2 abstract concepts that go in different directions, right? And if you go into more dimensions, you also have this effect that if you say, it actually doesn't have to be 90 degrees, everything between 88 and 92 degrees is still perpendicular to me, and then suddenly you get more perpendicular vectors in this less strict definition of perpendicularity. And I think it goes exponential with it. It goes in some mathematical relation when you go up with dimensions.
Hello. I also have a question related to dimensions. So why do we have different number of dimensions and different number of parameters? Because usually in machine learning, the number of parameters are the number of dimensions. But in your model, I think we had 7 billion parameters and around 3,000 some dimensions. So that I didn't understand.
Yeah. So the parameters is just the kind of soaking Dennis explained. So that one embedding influences the other embeddings. And if you do this multiple times, because with transformers you do this a lot after each other, then you will get not the same dimension there, but a lot more parameters that you have to choose because you apply this attention mechanism multiple times, if that makes sense. Yeah.
We have the layers that we have in transformers.
Yeah, so quite a lot of parameters there to finally get at something that mixes in all the semantic influences of all the words and bring them together.
Yeah, okay, thank you.
The number of dimensions you mentioned are the output dimension of the...
This is the, so...
Not the training dimension of the underlying model.
Yeah, so the dimensions are basically the dimensions the model puts out for each token that it would predict or that you want to embed.
Yep.
Sorry, the microphone is here. I just wanted to ask, you mentioned minimal number of dimension at one point. So you said the more dimensions, the more orthogonal vectors are, but there is some theoretical minimum, right? I guess, I don't know if I can formulate the question, but yeah, this one.
So
this
you're
one.
talking about this, yeah?
Right. But so there is some minimal dimension which the orthogonality is still enough, kind of, you're saying. And this is also rigorous, right?
So there are two components here. This is something you can prove mathematically, this formula. And to go in a bit of explanation here, it just says if you have this matrix earlier and you embed those queries and those emojis and calculate the distance, you want the distance of the ones that are denoted by 1 to be bigger than the smaller than the distance of that you calculated for the minus ones, which basically means you will have a higher probability of retrieving the ones that with 1 than the ones with the minus 1. And then you can apply a lot of mathematical theory and just say how probable is it for my matrix to always get the relevant ones first and then the not relevant ones. And that's mathematically proven, but this signed rank here is something quite hard to calculate for random matrices. And they did some assumptions on how these matrices look like, and then they came up in the paper with this polynomial that bounds the number of retrievable documents.
But does this have like a practical statement that I can make my neural net?
No, it's totally theoretically.
There's no minimal neural net at the end that could satisfy this.
It's just a lower bound that says if you want to have a perfect retriever, you need at least those many dimensions. And with less, it's just not possible to have a perfect retriever there.
But theoretically, it's possible to have a minimal neural net. Like you have this giant thing, and then you can make it smaller and theoretically smaller and smaller until you reach this, right? Is that the point?
Yeah, it doesn't say anything about parameters of your model. It just says something about dimensionality output of the model.
Okay, yeah. Thank you.
Meanwhile, we also have a question from the remote audience. Which vector database did you guys use, and how long did it take to create the embeddings, from simplest to the most complex ones?
Okay, we just have a FIS local database set up. So everything runs on the machine, and it's not that many emojis, right? We talked about 250 emojis and their corresponding embeddings. You can have this in memory, basically. And embedding is also quite fast. I don't know, for the big models in our compute cluster, let's say 250 emojis was 10 seconds, and I don't know, the other ones probably also 10 to 15 seconds.
Yeah. Yeah.
So everything is quite fast.
There was a microphone? Yeah, okay.
Do you know how the initial embedding of the emoji meanings was done? I'm wondering because if it's based just on the official description, I can think of a few emojis that are not really used how they're intended. Like the original emoji might be intended to mean tired, and then maybe it's mapped for tired, but it looks disappointed, and everyone uses it more like that. And while I guess the training can still map that emoji to the proper text messages, the original embedding will also affect how closely it's embedded to some other emojis. And if the meaning is interpreted wrong, that might place it in the wrong place, right?
Yeah, so for your first question, I don't know the training data they use, but what I could imagine, like training base model basically scrapes the internet for text, and their embeddings are encoded by their Unicode, not their meaning or descriptive text. So I would strongly guess, but not know, that they wouldn't replace all emojis, Unicodes by their meaning, but just use the Unicodes to train their model. Yeah.
And in the base models, it generally looked like they were all in the same place. Like a lot of emojis were just in a cluster. I mean, as far as the 2D representations go, which is absolutely not perfect, but you also see, like here we have a 0 point, like a high match, and they are all together. I don't know. Yeah.
Yep.
And there was a second part of the question that we forgot? Or has all of your question been answered?
No, that basically answers
Okay.
it, I think.
Yeah.
Maybe I missed it, but what do you use for the 2D projection? Like what algorithm?
RCA.
Okay. Yeah. Thanks.
Shortest answer. Nice. 3 letters.
Sorry, PCA, Principal Component Analysis. Yeah.
You were talking before about this theoretical lower bound for dimensions, but I was wondering, is there any notion of like an actual upper bound, a point where all of the complexity is captured, and if you go to more dimensions, this would be just not adding any new information, and you could just project to this like top level? Do you know what I mean?
Yeah, so for the research, that's the upper part, because they showed that with those dimensions, you can perfectly have the retriever work all of it, and every dimension you add on this will get you the same result, right? So the dimensions we showed are the theoretically bound for a perfect retriever.
All right. So it's more of an upper bound than a lower bound. It's you need that or less?
Yeah. So it's
right.
an upper bound on the first model that works, and the lower bound on every model before this doesn't work.
Right.
Yeah.
Okay. Thank you.
Thank you for this great talk. I have a question about the fine-tuning when you're training the model. When users are using emojis on their phone, they kind of all see the same list of emojis in the same order, and they tend to click on the ones they see first. So we have this position bias. Do you do anything to make sure that in the fine-tuning, the model also show diverse emojis, not just the popular ones?
Yeah, absolutely. By not using real data at all, generating literally every single data point that we have, and this means that we actually have the same amount of chat messages for every single emoji in the data set. So this is, to a degree, I mean, it's discussable, right? Probably if you implement this in a phone, you want the top 10 emojis first. You want them to have a bigger weight. You don't want to use the acorn emoji on every single message, even though it might be fitting. But this is definitely a concern. Yeah.
Coming back to the number of dimensions that you need, I think it would be very interesting to minimize, to look at much lower dimensions. So my guess would be, since 2 to the 7 is 256, that probably with 7 dimensions you could do a matching between text and emojis. But the problem is, of course, you don't have pre-trained models, and you can't really have an LLM with probably much less than 100 dimensionality of the token space.
Yeah.
Did you look? So you have already a pretty small model, but did you look around for even smaller models that you might cross-check with?
So the theory would suggest that we would be fine with 40 dimensions. That's not the parameters of the model. So I would think that you would still need a huge amount of parameters for the model to really catch the meaning and let all these embeddings soak into each other. That just requires a lot. of text understanding, and that's something you want a bigger model, but then the output embedding could be way smaller. And there is some research done into this, so some embedding models allow you to have more of the semantic mean or like broader concepts in the beginning of the vector, and then moving to more granular, fine semantic meanings in the back. And it's still a big vector that you get and a huge model that you have to compute the embedding in. But then if your application is optimized for search speed, for example, and I talked about like having to calculate a lot of distances, the fewer dimensions you have, the better your query time will be. And then you can choose one of these models and choose the appropriate amount of embedding dimensions to kind of speed up your embedding search. Yeah.
Do we have more questions online? No. All right. Any last questions?
So maybe the question is maybe too technical, maybe, but I'm just wondering with the limit on the dimension. No, just because I always thought, like, since you use like real numbers to encode some dimension parameter, I guess. On the computer, this would be a double or a float, so there is some limit. But in theory, you have like unlimited values, right, that you can use for dimensions. Like where would the argument be? Maybe roughly, if you can, like why you need to have more, even though one way it can be like anything, kind of.
Yeah. So maybe imagine a timeline, right? It's one-dimensional vector, and you could calculate a one-dimensional embedding there, and then your retrieval would look somewhere, maybe also lie on this timeline, right? And there's only one way of arranging everything. So each event on the timeline has to be done before or after another one. And with this, there are concepts that you can't show on this timeline. Although the timeline itself is a float or like a rational number and can be with as much precision as you want, but it will still have this notion of like coming before or after a certain thing. And so dimensions really help you there overcome this kind of closer or further away part, not the precision part itself, because it can only lay at one point.
So maybe also I would just like to, so I mean, in theory, I guess you could have like one dimension. If the distance is like divisible by 3, then it's essentially another dimension. And if it's divisible by 4 or something, you know, like you could kind of emulate other dimensions by like like how the distance is encoded, kind of.
Shall we maybe take this, because we have a coffee break now. So let's take this after the lunch, after the in the break. Yeah. So thanks a lot.
Yes, thanks for joining. Thanks for the talk, and have a nice coffee break and Big Tech Day.